Hello, everyone. I'm Ishan, and I'll be your lecturer today on today's topic about artificial neural networks. So, an overview of today's topics, we're going to discuss AI versus machine learning versus deep learning, look at the introduction to the inspiration behind and the origin of neural networks, discuss how computational neurons work, and you'll get an introduction to feed-forward neural networks and multi-layer perceptrons, how to train neural networks, applications, as well as limitations. So what is deep learning? You may have heard of these terms artificial intelligence, machine learning, and deep learning. And the thing is that machine learning is a subset of artificial intelligence, and deep learning in turn is a subset of machine learning. So artificial intelligence in general broadly refers to any technique that enables a computer to mimic human behavior. One such method for doing that is machine learning, and you guys have been introduced to classification and regression already, where you can use algorithms like KNN and SVCs, decision trees, random forests. These algorithms are able to learn without being explicitly programmed by us. They sort of learn on their own when they're given the data. So that's what machine learning is. And a specific part of that would then be deep learning, which is where we do that learning, we extract patterns, specifically using neural networks. So that's what we're going to be discussing today is neural networks. And what is a neural network? Neural networks are a type of machine learning model that uses layers of neurons to learn from data patterns and produce either categorical or continuous output values. And these signals are passed from neuron to neuron, and each neuron then determines whether to keep passing on signals to the next layer. So neural networks were inspired by our own neural networks, which are our brains. And there are some differences between the biological and computational neurons. So here's just a bit of a biological background so you can understand where all of this is coming from. As I said, neural networks were inspired by the biological systems of the human brain. And the fundamental component of the brain is the neuron. The neuron is a cell. So neurons in our brains communicate with each other to process information and make decisions. If you look at this diagram, you can see that the neuron as a cell contains a nucleus. The dendrites is where it's going to receive information from other neurons. And then that message is going to travel along the axon, which is the body of the neuron. And you can see it's insulated by myelin sheaths to ensure the potential travels through. And it's going to go to the axon, which is where it then sends out the message for other neurons to receive. So it travels in this diagram from left to right. There are three fundamental tasks of neurons. The first one is to receive information or signals. The second is to determine whether the information or signal should be passed on to other neurons. And the third is to communicate signals to other neurons or target cells. So you can see in this diagram over here, we have, this is the end of one neuron. This is the beginning of another. And this over here, this gap between them is called the synapse or the synaptic gap. And the idea is that the previous neuron is going to release neurotransmitters, which carry the message forward to the new cell, the postsynaptic cell. And when enough of these neurotransmitters bind to the receptors on this postsynaptic cell, that's when the message is now going to be carried through the postsynaptic cell onwards. So the neural network process, the way that it works is that we first create the model, and initially all of its weights, its parameters that it's eventually going to learn, those values are going to be essentially randomized to start off with. Then what we're going to do is forward propagation, where we feed the model some input data. That data is going to travel through all the layers in our network all the way to the very end and produce some predictions. And then what we do is we look at the prediction, we look at the actual value, and we compute the loss or the error. And using that error or loss from our outputs, we're going to try to minimize that loss function and minimize the prediction error by now going backwards, back propagating, and changing the model's weights to minimize that loss function. And an example of that loss function would be something like mean squared error or mean absolute error. And there are some other errors that we'll be working with. Here's a diagram of a feed-forward neural network. You can see that it's comprised of multiple layers. The first layer is what we call the input layer. In the middle, we have the hidden layers. And the last layer is the output layer where we get our answer. In a feed-forward neural network, the information only flows forward through the network, so from the first layer to the last layer. It is used when data is not sequential and is not time dependent. For these types of data, we use a recurrent neural network. But in this case, we're just going from left to right. So how does a computational neuron work? The idea is that we have a neuron over here, and it's going to receive some inputs demonstrated by these orange arrows over here. It's going to receive some inputs from neurons in the previous layer. And it's going to take those inputs and do some computations to process them and produce its own output. And before I get into activation functions, let's take a look at this diagram over here, which now has some labels. So X1, X2, and X3 are the inputs that we're receiving from our previous layer. And we're not just going to take them and add them all up together to get our new output. We're actually going to multiply them by a weight. So that's what these connections over here, that's why they have these W's on them. W1, W2, and W3 represent the weights. So the idea is that we're going to do a weighted summation of the inputs from the previous layer. So for example, this neuron might have an input of 1, and it might have a weight of 1, whereas this neuron over here has a weight of 0.5. So this neuron, the top one, is weighted more heavily than the middle one. And that's basically what the weights allow us to do, is determine exactly how much of that input we want to pass on to our neuron. So for example, if the weight is 1, we're passing in all of our input x1 to the neuron. If our weight is 0, 0 times x1 is 0. So we're passing on none of our input from this neuron to the current green one shown over here. So that's one part of the processing that we're doing of the inputs. In addition to doing this weighted summation shown over here in this equation by x1 times w1 plus x2 times w2 plus x3 times w3, we also have a constant term called the bias, which we're just going to add on to this weighted summation, and that's going to be a part of our output. So you can see over here the bias b, and that can be a value like 0.5, 0.75, whatever. It's just a constant number that does not depend on these inputs, x1, x2, and x3. So the idea is that we take this weighted summation plus the bias, and then we get a value called z. And then what we're going to do is we're going to input it into an activation function. So activation functions are how neurons transform the input data and determine what to output. And this over here gives a more mathematical expression of what that looks like. Like I said, we have our weighted summation of the inputs, x1 times w1. We add on our bias, and then we take that whole sum and we input it into a nonlinear activation function. And whatever the activation function g, or in this diagram over here, f, whatever they output, that's going to be the output for this neuron. Here's an example of a very basic activation function. It's a threshold or binary step activation function. So you can see that if the input is negative, our function is going to output a value of 0. If our input is positive, our function is going to output a value of 1. And this ensures that there's only 2 output options available. So let's say, for example, we did our weighted summation, and we did our bias plus our weighted summation, and we're getting a negative value. Basically, what that means is when we feed our negative value through this particular specific activation function, we're going to get an output value of 0. That's what this neuron is going to output to the neurons in the next layer. It's going to output 0. But if our weighted summation plus our bias is positive, we're going to output a value of 1. So you can see how the activation function can sort of be used to control what exactly our neuron will be outputting. In this case, if it's negative, it's saying output 0, which is pretty much like nothing. Otherwise, if it's positive, it's saying output 1. Here are some other very popular activation functions. We have the sigmoid function, shown over here in blue, and its derivative is in orange. We also have the hyperbolic tangent function, or tanh, and the rectified linear units function, or ReLU. ReLU is a very popular activation function. You can see over here its equation is quite simple. It's just a maximum of 0 and our input. So the importance of activation functions is that they introduce nonlinearity into our neural network. So for example, if we just had a neural network that consisted of equations like y equals mx plus b, even if we did have a ton of neurons, that we had a ton of weights and a ton of biases that we were adding and multiplying, it's still linear. So if you look at this example over here, it's a basic 2D example where we have this green and red data, and we'd like to maybe do some classification with it. If we had a basic y equals mx plus b algorithm or approach to classify the data, it isn't going to work very well because you can see the data is in a very weird shape. But once we introduce some nonlinearity into it, it allows us to approximate complex functions a little better. So here's an example calculation of the act of that a neuron would perform. We have our three inputs from the previous layer. So neuron number one from the previous layer is giving us a value of 0.9. Neuron number two is giving us a value of 0.2, and neuron number three is giving us a value of 0.3. And you can see that they have different weights. So the first neuron has a weight of 2, the second has a weight of 3, and the third's connection has a weight of -1. And if you look over here, z equals, this is where we're doing a weighted summation. So 0.9 times 2 plus 0.2 times 3 plus 0.3 times -1. And then, like I said, we have our bias over here, which is a constant, and it's independent of our inputs from the previous layer. So we add that on, so plus 0.5, and we get a value of 2.6. Before we pass that value of 2.6 on to the next layer, we're going to pass it through our activation function. And when we pass it to our activation function, f of z, we get a value of 0.93. So now the neuron would output the value of 0.93 to the next layer. And an important thing to note is that in a feed-forward neural network, a neuron is not connected to neurons in its own layer. So if you look at S1 and S2, there are no connections between them. Instead, we have connections from X1 to X2 going into S1, and we have connections from S1 going into S3 and S4. So that's where the neurons output is going to go. It's going to go into the neurons in the next layer. Now let's talk about multi-layer perceptrons, or MLPs. So multi-layer perceptron is just multiple layers of neurons stacked together. And the layers of neurons allow for much more complicated computations and learning rather than just having one hidden layer. In a feed-forward neural network or multi-layer perceptron, no layer's output depends on itself. So that's what I just discussed a few seconds ago. And there are no connections between neurons in the same layer. Here's the diagram of a MLP structure. We have the input layer, a hidden layer in the middle, and then the output layer. And all of these are connected by weights, which we discussed. And this over here is just another example of the weighted summation. We have our bias over here plus the weighted summation of the inputs times the respective weights. And another thing to note is that each neuron is going to have a different weight for a previous neuron. So for example, Z2 has weight W1, 2 coming in from X. Z1 is going to have its own unique weight that comes in from X1. And it's going to have its own unique weight that comes in from X2. So there are a bunch of different weights and biases associated with a layer. And in this example, we have what's called a fully connected network, in which a given neuron has connections to all the previous neurons in the layer and all the following neurons in the next layer. You can see there's 3 connections going into Z1, 2 connections going out of Z1. In one of the previous images, there was only 2 connections going into Z1, even though there were 3 neurons. So that was not fully connected, but this one is. And it basically means that you have a large neural network with more parameters to learn. So like I said earlier, the weights in a neural network are going to be randomly initialized. One way that you could do this is with a class that Keras offers called Glorat Uniform, where you provide some parameters, some optional parameters, and then it generates a uniform distribution. And the idea is then that you could use this initializer and pass it into your your neural network layer. And the important thing to focus on over here is this last line that says layer equals tf.keras.layers.dense 3. This is how we create a neural network layer. Basically, what we're saying is we have a dense layer where there's going to be 3 neurons in that layer. And this Keras initializer is an optional parameter if you wanted to define how you want to initialize the weights in that layer. So let's look a little more at the MLP structure. The output layer is going to produce the classification predictions using the softmax function. And the softmax function is just one of many activation functions that we can use. It wasn't on the previous slides. So what we're going to do is pass the data in to our input layer. It's going to go through our hidden layers. It's going to go then to our output layer. And then the output layer is going to calculate its outputs, and it's going to pass the output for each neuron to the softmax activation function. And what the softmax activation function does, when we use that function, the output values are going to be mapped to a probability distribution for different classes, and they will all add up to 1. And the class with the highest probability is the classification that we're interested in. So for example, let's say you wanted to classify apples, oranges, and bananas. Those were the 3 different classes that you had. And let's say that each neuron represented the probability, the output for each neuron represented the probability of it being an apple, the probability of it being an orange, and the probability of it being a banana. So now what's going to happen is when we get the outputs from our last layer, those 3 values represent the probability of it being an apple, orange, and banana, and they're all going to add up to 1. So now if we want to see what our neural network classified the input as, whatever the input was, maybe it was numbers, maybe it was image, whatever it was, if we want to determine what our neural network thought the image was, we simply look at whichever index had the highest probability, the highest number. So let's say it was the middle index that had the highest number, the middle neuron had the highest output, then we can say that this was an orange. That's what the model classified our image or our data as. It classified it as an orange. So that's where we'd use the softmax activation function for classification. And if we want the outputs from the neurons to all add up to 1. So here's an overview of how we train a neural network. We have our weights in the neural network that are continually updated in order to minimize the error. And that's like what I said through the backpropagation. And the way that we do that specifically is by using a cost function or a loss. Remember, this is the error I was talking about. So maybe you could use mean squared error, you could use mean absolute error, you could use cross entropy. There are a couple of different ones we'll talk about in a bit. And then what you do is gradient descent. So in gradient descent, if you're familiar with calculus, gradient descent uses calculus to look at the loss function, calculate the derivative, and then determine how much we should move in each direction. And then this information is then back propagated to the neural network so we can update the weights and the biases and the other parameters. And there are 2 different goals or outputs. So for example, we could have regression, which would output continuous values for our output. On the other hand, you could have classification, which is categorical values for our outputs. So we have to keep these tasks in mind when we're determining what loss function to use. Because in our neural network, there are lots of things that we can play around with. So for example, with the k-nearest neighbors algorithm, one of the main things that we could play around with for that algorithm is the value of k, how many neighbors we're going to be inspecting. But with neural networks, we have a lot of different things we can control. We have the number of layers in our neural network. We then have the number of neurons in each of those layers. We have the activation function that each layer is using. We have the loss function that our neural network is going to use in order to achieve its goal more successfully. So we have a lot of things that we're controlling. That's why we want to pay attention to whether we're performing a regression task or a classification task when choosing our error function. So the model's predictions are evaluated using the cost function that determines the error. And here are 2 examples. Like I said, mean squared error is a very simple one. It's basically where you look at the actual, you look at the predicted, and then you look at the difference between the 2, square them, and add that all up for each of the samples. And then we also have cross entropy, which is used for classification. And the goal is for learning, when the neural network is learning, the goal for it is to minimize these functions, to minimize the loss or the error. And the loss values for training and validation may be different. So I don't know if you guys learned about training and validation already, but the idea is that the training set is what our model is going to use to update its weights and biases and to actually learn. That's what it's going to be using to propagate through the network, look at the loss function, look at the error, and then back propagate to adjust the parameters. That's what it's actually learning from. However, during the training process, we might also want to see how our neural network is performing on data that it hasn't seen before. That's where our validation set comes in. The idea is that we're going to have our neural network training on the training set. It's going to be adjusting its parameters and doing all that stuff based off the training set. And then we're also going to have it look at the validation set and just see what error and what accuracy it obtains on the validation set. It's not actually going to use the validation set to then go back propagate and learn and adjust the parameters. It's only using the validation set to tell us what accuracy and what error and what other details we're interested in, how it performed on the validation set. And what this allows us to see is if the validation loss is a lot greater than our training loss, that means our neural network is overfitting on the training data. It's memorizing the training data very specifically. It's adjusting its parameters so that it nails down that training data. But then when we give it the validation data, which it does not learn from, which it just simply evaluates on, when we observe the validation loss, that's a lot higher because our model is overfitting. And similarly, if our training loss is very high, that means our model is underfitting. So that's why it's useful to use the validation set in our training process to see how our model is performing and generalizing to the validation data, which it is not learning from. Here's a diagram of how gradient descent works. It's very simple. The idea is that in gradient descent, we're going to calculate the gradient, essentially the slope or the derivative, if you take in calculus, of a function. And then we're going to move in the negative direction and update the weights so that we can reach a minimal amount of error. So in this diagram over here, you can see that we have a slope. It's a positive slope, which means that we keep on moving right in the positive direction. Our loss function, which is represented by J, our loss, our error, same thing. Our loss is also going to be increasing. That means if we move in the negative direction, so if we move in the negative X direction, or in this case, I guess negative W, our error function or our loss function is going to be decreasing. And the goal for any neural network is to find this global cost minimum. That if you achieve this global cost minimum, that means your error for the neural network is as low as it can possibly be because it's the global minimum. And we want to keep on moving in this direction until we achieve this global minimum. However, more realistically, what may happen is, let's say we start off over here. We see that we have a negative slope, which means that at this point over here, this starting point shown by the circle, if we want to minimize our loss function, because it has a negative slope, we're going to move in the positive direction to decrease our function's value. So it may jump over here. It may jump to this X coordinate over here. And then from this X coordinate over here, it has a positive slope. So it says to minimize our loss, we have to move in a negative direction. We're going to have to move left. And then it jumps over here. And as our neural network trains and updates the gradient, the idea is that we may want to start taking smaller jumps because hopefully we should be getting close to our answer. So that's why over here you see the arrows are getting smaller. Likewise, over here, the jumps are getting smaller. But you can see that what ends up happening in this case over here is that we find a local minima, not the global minima. Because from the starting point where we began, our slope was negative, which means that to decrease our loss function, we wanted to move right. But we didn't see the bigger picture. We didn't see the bigger picture, which was that if we move it a little bit left, and let's say we came over here and we started here instead. If we started here, we would see that our loss function is positive. I mean, our derivative or our slope is positive. which means that to minimize it, we want to move left. And then if we move left, we would have achieved the global minima sitting over here. And that's the difficult thing about trying to achieve this minima, trying to calculate the gradient and trying to minimize the loss function is that when you have a ton of variables, imagine instead of having one variable over here, instead of having x, we had multiple variables. So in this example over here, this looks like a really weird loss function, but in reality, there's only two variables. Our x and y are the two variables that we have for our neural network. Let's say those are the two variables it's trying to learn from. That's our input. And the z variable is simply our loss function. So for example, at a given x and y coordinate over here, we have a fairly low loss. At an x and y coordinate over here, we have a high loss. As we increase the number of variables, it becomes even harder and harder to find the global minimum. And that's why it is difficult to achieve, to train a neural network that has perfect results. Now, with gradient descent, like I said, what we're doing is we're passing the data, or we're taking our input and we're feeding it through the network. And then that's when we calculate the gradients and backpropagate. Some things that we can do are we can decide how many samples to train on before we calculate the gradient. So for example, I might have a data set, a small data set of 50 images, or 50, let's say 50 images. What I can do is I can have a batch size of 5, which means that my model is going to take 5 inputs. It's going to take 5 images as inputs, feed it through the neural network. And after it's done with those 5 inputs, then it's going to calculate the gradient. Then it's going to do the backpropagation. So basically, it only does the learning. It only does the updating after it has 5 images. So it's going to take that first batch of 5 images, feed it through, then make the adjustments. Then it's going to take the next batch of 5 images. It's going to feed it through, look at the loss, look at the error, and then it's going to determine what to update based on that batch of 5 images. So that's what a batch is. It's after how many samples we update or calculate our gradient. Stochastic gradient descent is a specific type of gradient descent in which we're going to have batch sizes of 1. So we're going to look at a single sample, pass it through, and then update our neural network. We're going to take another image, pass it through, and update our neural network. And some things to note about this approach is that it introduces randomness and noise. Let's say I'm training a neural network to recognize cats, dogs, and horses. A cat is pretty different from a horse. So let's say I take my image of a cat and I'm doing stochastic gradient descent. I pass it through my neural network, and then I update the weights, I update the biases. Remember that diagram of all the lines between the neurons? I update those lines with the correct numbers so that when I do my calculations, when I do my multiplication, when I do my addition, I get an output saying cat. So I take that cat image, I feed it through, and I make those updates. So the equation will give me an output of cat. Now let's say I take, and the next sample is an image of a horse, and I pass that through my neural network. And because I'm doing stochastic gradient descent, after I pass that sample of a horse, I'm then immediately going to calculate the gradient and update my weights. And because a horse is large, it may be a different color from the cat, different shape, all sorts of different things. Now, when I calculate the gradient, it's going to be making quite a bit of changes compared to if I had another cat image I was feeding in. So because you're updating it after each single image, that's what it means by noise. There's going to be like a lot of variation, a lot of changes happening with stochastic gradient descent. With mini batch gradient descent, we're basically going to be calculating the gradient after batches of samples. So that's where we have we have multiple images or multiple rows of data in our batch, and then we calculate the gradient, which is what we talked about earlier. So that's how gradient descent works. Its goal is to minimize the loss function. And let's see, then backpropagation. This is the step where we're actually going to use the gradient descent. We're going to calculate our gradients and then feed that information back through the neural network in order to adjust the weights. And remember, the weights are what we're multiplying the inputs by in that weighted summation shown over here. So we're going to update the weights, we're going to update the biases, we're going to update all of this information um, in order to minimize that loss function. And this is what I was saying, where the neural net, the actual loss function is going to have several variables because we have a lot of weights, we have a lot of biases in our neural network. All of these parameters need to be updated when we're doing backpropagation. And that's the idea of backpropagation. It just looks at our loss function, determines what we need to adjust our weights by, and it backpropagates through the network and makes those adjustments. So here's an example problem, which is determining, will I pass this class? And this is a very simple model in which we have two features or two inputs. The first input is the number of lectures that you attend, and the second input is the number of hours that you spend on the final project. So over here, we have a graph. The x-axis is the number of lectures you attend, the y-axis is the number of hours you spend on the project, and then the red and green symbolize whether you fail or you pass. So now given this new input over here, the question is, will you pass the class? Here's the diagram of exactly what the loss would look like. So we take our input 4, 5, and we pass it in. So for example, x1 would be 4, x2 would be 5. We take those numbers, we multiply them by the weights, and then z1 would get that value, x1 times its weight plus x2 times that weight plus the bias. Z2 would similarly receive the same sort of equation, and Z3 would receive the same sort of equation except with different weights, different weight values. And then we do the same computation over here where we do the weighted summation, add on the bias, pass it to an activation function, and then we pass it on to our output. So now the loss of our network, the way that we compute the loss of our network is by measuring the cost incurred from incorrect predictions. And we pass in our predicted value and our actual value into the loss function, and then calculate that loss. So for example, the loss could be mean squared error, it could be binary cross entropy, whatever the case is, we're just going to pass in our predicted value and our actual value. This shows it in a little more detail. The empirical loss measures the total loss over our entire data set. So once again, over here, we have this this function representing the cost. And what we're doing is, what this sigma notation over here means is that we're going through every single one of our inputs, and then we're calculating the loss for each of those inputs. And then when we calculate the loss for the inputs, we're summing them up over all of our samples, and then we're dividing by n to get like the average loss for each of the samples. And with binary cross entropy, this can be used for, cross entropy losses can be used for models that output a probability between 0 and 1. As you can see over here, this is its specific loss function. This is what it looks like. It uses logs to compute the loss. And you can look into that in more detail later on if you want to. And the idea is basically, you're going to be penalized if you're closer to the actual value than if you're farther away. Because you have to remember, our neural network, depending on the activation function we're using, in this case, it's outputting values between 0 and 1. It's outputting continuous values like 0.1, 0.8, 0.6, when in reality, we want our outputs to be 0 and 1. So the way that we're calculating the loss between our outputs and the actual values is through this function over here, where if our output is fairly close to the actual value it should be, well, then we're going to have a lower loss value or a lower error value. But in this case, you can see 0.8 is quite far away from 0, and 0.1 is quite far away from 1. So that's why we use logs to like sort of penalize the values that are farther away. And 0.6 is closer to 1 than it is closer to 0. So in this case, our model did fairly well in calculating a value that is closer to the actual value that it should be. Mean squared error is shown over here. Once again, it's a very simple function where you look at the actual value, the predicted value, you take the difference, you square them, and then you sum that up for all the samples and then divide it by the number of samples. This can be used with regression models that output continuous real numbers. So you can see over here, our expected output that we wanted for our for this task over here was 0 or 1. For this task over here, it can be continuous real numbers like 90, 20, 95. So in this case, we're going to use the mean squared error loss instead to calculate the error between what our model outputs and what the value should actually be. And in this case, it's basically what it does. It's going to penalize values the farther away they are. So example, if you look at 1 and 2, the difference between 1 and 2 is 1, and 1 squared is 1. But now if you look at it at 1 and 6, the difference between 1 and 6 is 5. If you square 5, that's 25. 25 is a lot larger than 1. So we're penalizing our function, or I mean, we're penalizing our neural network more the farther away that its values are from what we expected. That's what mean squared error loss does. Similarly, if you were to take it to the fourth power instead of the second power, it will penalize it even more. Basically, the farther away your values are, it gets penalized even more than it would if it were closer to the actual value. So what can we use neural networks for? We can use them for handwriting recognition, financial prediction, data compression, voice filtering, predicting protein structure, a whole bunch of different things, not limited to what's shown on the slide. And there are two main types of applications. So like we discussed at the very beginning, neural networks draw inspiration from the brain. So because of that, we can use them to build models of how real brain works. And then we can understand the nature of human intelligence. We can formulate better teaching strategies. We can basically build a neural network that models a human brain and then play around with that neural network and test it to see how our brain would operate under certain conditions. So it can be used for that sort of research. Similarly, we can use it for artificial system building, for building efficient systems for real world applications. So for example, for maybe providing recommendations on a website like Amazon or YouTube, or doing classification of cells and determining whether certain cells are cancerous or not. So there's these two main types of applications. One is modeling the brain, and the other is actually building systems for the real world. So with brain modeling, we can compare brains with neural network models to improve development. For example, children's development versus models that simulate both maturation and learning. We can use it for adult performance, so analyzing adult performance versus models performance, and then other things like brain damage and neuropsychological deficits. Models can tell us about how the normal brain would operate, tell us more about normal brain operation than normal performance. There are also some use cases, a ton of use cases of deep learning in medicine, and you can check out this link later. And there are some limitations of neural networks. So whereas for a decision tree, if you're using scikit-learn's decision tree class, you can actually generate a diagram of what the decision tree is doing. So it's pretty cool, actually. Like, let's say your decision tree has a couple of different variables that it's looking at. You can actually generate a diagram that shows at each step what variables it's looking at. And if it's looking at, like, let's say variable A is greater than 5 and variable B is less than 3, then go in this direction. You can actually see that it'll generate a diagram for you. But with neural networks, they're often black boxes. They're difficult to interpret and understand how exactly this decision-making process is happening. And there are also a ton of parameters in a neural network. Like we saw some very basic examples of a neural network with some weights and biases. In reality, for neural networks that are performing complex tasks, they're going to have several layers. Each of those layers may have hundreds of neurons, maybe even thousands. So there's a lot of stuff going on, and it's very difficult to understand exactly what those computations with those variables mean. And overfitting can be common, where it trains very well on the training set, but it does not generalize to data it's not seen before. And overfitting can be hard to solve in these instances. So that's why it's useful to use a validation set to see how your model is performing as it trains. Now, there are some things that we can do. So for example, one thing that we can do for regularization is dropout. And the idea behind dropout is that we're going to randomly decide not to use some nodes, and this prevents overfitting. This prevents the model from relying on any one particular node. Um, and just as a fake example, let's say that this node over here, Z11, was starting to become very important, by which I mean these weights over here to the following layer, these three weights, let's say they were very high. Let's say like 100, 100, and 100. Whereas for something like Z1, comma 2, its weights were like 1, 0.5, 1. So the Z1, comma 1 was starting to influence a lot of influence over the next layer. And one thing I should have noticed over here is for the notation, the first one indicates what layer it's in. So that all of these neurons over here are in layer 1. That's why they have a 1 in the beginning. And the number and the comma is what neuron number they are. So this is neuron number 1, this is neuron number 2, this is number 3, this is number 4. That's notation for them. Anyways, going back to what I was saying, let's say Z1, comma 1 is becoming very important and its weights start to become really large and it's exercising large influence over the next layer. Dropout allows us to ensure that we're not having our model rely on any one particular neuron or node. And this can help avoid overfitting on the training data. So what we would do in our code is we'd have a dropout, we'd have our neural network, we'd be adding our dense layers like we saw earlier with the keras. We'd be adding our dense layers specifying how many neurons we have in each layer. And then we'd have a dropout. We'd use a dropout class to specify like what percentage of nodes we'd like to drop. Another thing that we can do is early stopping. So the idea behind early stopping is to automatically stop training for us once we achieve a particular loss point, or like let's say our validation loss. So you can see over here, we have our errors, we have the validation set and training set. So you can see over here that our training set's error keeps on decreasing. And the reason for that is because now it's at some point it's starting to overfit. It's basically starting to memorize the training set data. And that's why it's performing so well, because it's memorizing the data, so the loss is decreasing. Meanwhile, for our validation set, it does decrease to an extent. It's doing well, it's learning, it's performing well and generalizing on data it hasn't seen before. But now there comes a point where it starts to become so specific to the training data that it's learning from that our validation loss starts to increase again. So we can use early stopping when we're training to say, like, if our validation loss starts decreasing, if our validation loss starts increasing again, or if our validation accuracy starts decreasing, then let's stop. This is a good point to stop because we want to avoid overfitting and we don't want to keep on training our neural network and having it overfit, and our validation set accuracy or error keeps on worsening. So that's the idea behind early stopping, is that we can specify those kinds of functions and those kinds of values to stop while our neural network is training. Now we're going to do a walkthrough of a neural network on Google Colab. There's two examples. The first one involves some Titanic data, but there are some issues with the data format. So we're just going to go ahead and click on the second link. And it should take you to this notebook over here. One thing to note is that your changes will not be saved. That's why if you want to be able to come back to it and make edits, you should click on the copy to drive button over here. But basically we'll be doing, the code for us has already been written for us. So we'll just have to run the cells and I'll be explaining what it does at each step. So in the first step, we're going to be importing some important packages like NumPy and Pandas, which allow us to handle our data. We're also going to be importing our sequential model. So this is how we're going to define our neural network as a sequential model. And we have matplotlib for doing some visualization. So we can go ahead and click run anyway and run this cell. Now, while that's running in our second cell over here, we have some data scaling going on, which you don't have to worry too much about. But if you look over here, you can see that we have two variables. One is our training data frame, and the second one is our test data frame. So let's go ahead and run that. Once again, you don't have to worry about how the scaling is going on, but it's basically so that our neural network will receive values from 0 to 1. That way it works well, because you don't want to be giving it like values ranging from 0 to 100,000 or 0 to a million. It's better to keep it more standardized. That's why we're doing scaling, to keep it between 0 and 1. And the idea now is that we're ready to build our neural network and begin the training process. So this over here is the code that we use to create our model. And I'll explain it line by line. So first we say that our model is going to be of the sequential class. Essentially, the sequential class allows us to add layers to our model. So that's why we say model equals sequential. It's a sequential network. And then we add our dense layers by saying model.add. And then the first parameter for dense is how many neurons we're going to have in that layer. So this is a very basic neural network. We only have one input for our first layer. And then you can see that we're specifying the activation function using this parameter activation equals. And right now we specified linear. You could also say something like ReLU or softmax. In this case, we're just using linear. You can even see this tanh over here. Another one we could use is sigmoid. And you can play around these activation functions later in a bit just to see how it affects the model's accuracy and performance. But the first layer is our input layer. We have one neuron. Then we have three hidden layers. Each of these hidden layers has two neurons, and we've also defined the activation function. Um, and then our last layer has one output because it has just one neuron, and it's going to be a linear activation function. So this is where we define the architecture for our neural network, 5 layers, and we've specified how many neurons in each layer as well as the activation function. Now, the next thing that we want to do before we can jump into training immediately is we've got to specify our loss, our error function, whatever you want to call it. And the way that we do that is by saying model.compile. So you say model.compile, and there's a parameter called loss. In this case, we've done mean squared error. Like I said before, there's a lot of different things that you can do, like binary cross entropy. So you can type that out, binary cross entropy, and so on. And there's this thing over here called optimizer, which we didn't discuss in the slides. And what the optimizer does is it determines, this is the actual thing that does the gradient descent and decides what direction to move in and how much we should move in that direction. So in this case, we're using the Atom optimizer. Some other ones that you might hear about are RMS prop and Adagrad. So once again, you can play around with these optimizers in a bit and see how it affects your model's performance and training. Right now, we're going to use the Atom optimizer. And the rest of this is just some code that the person wrote to load the training data. And the next important step over here is model.fit. So just like you did in Keras with the KNNs and the SBCs, we use model.fit. We pass in our X set, our Y set. And now there's another, we can delete this verbose equals 0. We don't need that. But there's this other parameter that we have here that's also unique to neural networks, and that's epochs or epochs. And this basically tells us how many iterations of our data set we should go through. So with our KNN or SBC, we only really went through one iteration of our data set. But with our neural network, what's going to happen is that it's going to go through our data set. It's going to go through, like, let's say all the images or all the rows in our data set once, and it's going to do it a second time and a third time and a fourth time and a fifth time. It's going to keep on going completely through our data set, how many ever times we specify over here. So we can say epochs equals 50. This is also where I believe you can specify the batch size. So you could say a batch size equals, I'm not sure how large this data set is, but maybe you could say something like 30, 32 is pretty common to be used, 32 or 16 or 20, whatever you want, or even 1 if you're doing stochastic gradient descent. So that's what we do in model.fit. We pass in our data as well as the number of epochs. Originally it was 5,000. 5,000 is a bit big, but I suppose our data set is small. Anyways, let's just run this cell now and see what happens. And you can see it's actually speeding through the data because I think the data set's fairly small and there's not that much data for it to go through. It's actually doing it in 6 milliseconds. And you can see, let's start off at the top. We have our first epoch. So this is epoch 1 out of 50. So it's going through one whole pass of our data set. And in this case, it starts off with a loss of 0.4330. If we scroll down a bit, so we go to epoch 20, at this point, it's done 20 passes through our data set. So it's seen all the data in our training set 20 times. Now the loss is 0.3072. And if you scroll down all the way to the very end with 50 epochs, it's still decreasing, which is good. It's at 0.1797. Because it's running so fast, you can run this for 500 epochs if you want. And you can see it's going through it fairly quickly. When you have more data, as well as a larger neural network, it can take several minutes, maybe even an hour for one epoch to go through. Like there's one example where I was creating a generative adversarial neural network to create human face images. So this is a special type of neural network that generates images. That one was taking like an hour per epoch because my data set was large and the neural network itself was also very large. Um, but yeah, this is a basic example of how to create a neural network with and add dense layers, as well as specify the activation function, specify the loss and the optimizer, pass in the training data as well as the test data, pass in the training data, the input data, as well as the expected output data, and then the number of epochs. And if you scroll down to the down to the cells below, if you want to evaluate your neural network on new data without training it, you can use model.evaluate. And then you pass in your inputs and the expected outputs. And then you can see here that it's going to return the mean squared error because we specified that the mean squared error is going to be the loss function. So that's why when we print out MSE, we get the mean squared error is 0.0519. And this is how it performs on the data it's never seen before. So that's a pretty good low mean squared error to have. And over here, we can plot, this is just plotting the data. Again, this is a very simple data set with just X data and some Y data. And that's about it for this neural network example. This is the main cell over here. And like I said, this cell over here has an example with the Titanic data set. So this is something that you can play around with for yourself and explore. Um, the thing is that the data isn't already loaded into it, or it looks like it is, train.csv and test.csv. So you'll have to make some modifications to this Google Colab notebook. For example, deleting that so that says train.csv, and then deleting that so it says test.csv, and it's loading the right data. This is another notebook for you to explore. Now, your homework assignment is going to be to download the data from the Drive folder and reshape and normalize the data as needed. And this is the data, this is where you can collect data from. And what you have to do is build a neural network classification model with input, hidden, and output layers using the Keras sequential methods we discussed in class. Remember, you say model equals sequential, and then you can use model.add dense, model.add dense, and keep on adding dense layers. So you've got to train and test your neural network and observe the classification accuracy on the testing set. So once again, you would use like model.evaluate to see how the model performs on just some given data. So that's your homework assignment. And that's it for today's lecture on neural networks.